Before, people would travel distances either by foot, horse-drawn carriages, bicycles, cars, or ships, until air travel was made possible. Air travel is the fastest and one of the most important modes of travel today. In view of the efficiency it provides, the invention of airplanes by the Wright brothers led to global interconnectedness as more and more people utilize this mode of travel as the economy continues to grow rapidly. However, as the demand increases, airlines face difficulties that result in delays of flights. One of the most common problems that occur is the delays due to insufficient boarding gates as airlines share the same resources. To avoid this kind of delays, the airlines have to schedule flights at different gates such that there are no flights with the same or overlapping time interval in one gate. But, what methods should they do to make this possible? Let us discuss the concepts of graph theory. First, let us define what a graph is. A graph is a set of ordered pairs containing a vertex B and an edge E, denoted by. The vertices are also called nodes or points. The edges are the lines connecting the vertices, also called the links or connections. In this graph, it has a set of vertices and set of edges. Some of the properties of a graph are order, degree, incidence, and adjacency. The order of the graph denoted by is the number of vertices it contains, while the size of the graph denoted by is the number of edges. In the given graph, its order is 5 and its size is 5. The degree of a vertex is determined by the number of edges connected to it. It is also called the valency of a vertex. In the given graph, each of the vertices has degree 2 because they all have 2 edges connected to them. The incidence vertices are incident with an edge. If the edge is at V, meaning that a vertex is an incident to an edge if they are connected. Adjacency vertices are said to be adjacent to one another. If they are connected with an edge, the degree of the vertex is the number of vertices adjacent to it. For example, in the given graph, vertex 1 is adjacent to vertices 2 and 5. Vertex 3 is adjacent to vertices 2 and 4. You might be wondering, how can graph theory help in solving the problem? As such, the graph theory concept to be used in solving the problem is graph coloring. Graph coloring is a way of coloring a specific vertices or edges in a given graph such that vertices or edges with the same color must not be adjacent to each other. Such a graph is also called a properly colored graph. In this, we will use vertex coloring, which is the process of assigning colors to each vertex. The K-coloring of a graph G is a vertex or edge coloring that assigns each vertex or edge of G with one of the K possible colors. If graph G can be properly colored using the K colors, then G is a K-colorable graph. For example, the given graph has 3 colors, red, yellow, and blue, which denotes K is equal to 3. Since it is also a perfectly colored graph, we can say that the graph is a 3-colorable graph. The chromatic number of graph G, denoted by the Greek letter G, refers to the minimum number of colors needed to color the vertices or edges of the graph, so that no 2 adjacent vertices or edges have the same color. It is also simply the smallest number of colors required to color a graph properly. In the given graph, we know that it is a 3-colorable graph. Since it is impossible to color the vertices with less than 3 colors, we can say that the minimum number of colors required, or simply the chromatic number of the graph, is 3. If K color is equal to the chromatic number, then G is a K-chromatic graph. In the given graph, we know that K is equal to 3, and its chromatic number is also to 3. It denotes that the graph is a 3-chromatic graph. Using graph coloring, we can determine how to allocate airport gates for flights to prevent or minimize delays caused by queuing. This data set retrieved from the official website of the Manila International Airport Authority, or MIAA, shows flight schedules for all four Ninoy Aquino International Airport terminals on May 6, 2022. From this, we will use the dataset of passenger flights on Terminal 1. To process and plot the dataset, the arrival section was first considered. To determine the layover duration of the airplanes, arriving flights and their corresponding departure flights were identified since flight numbers change upon departure. Some flights do not have a corresponding arrival flight number in the departure section. This means that the flights arrived the day before and are not reflected in the dataset because the dataset is only for one day. Those flights were plotted to start from 12 a.m. and flights that depart to the next day were plotted until 12 a.m. of the next day. There are 24 flights identified from the data plot in the flight schedule dataset. One flight is considered as one vertex and named as vertex 1, 2, 3, and so on respectively. Therefore, there should be 24 vertices representing the 24 given flights. The edges were identified as flights whose layover time overlaps in the flight schedule dataset. We can consider coloring first the vertex with the highest degree. In the graph, we will assign color first to vertex 24 since it has the highest degree. Then, we will assign colors to the other vertices. We must ensure that vertices that are adjacent must not share the same color because each color represents one gate. This indicates that flights with overlapping time intervals cannot be assigned to or use the same gate because a gate can only accommodate one airplane at a time. As we can see in the graph, we only needed 7 colors to ensure that no adjacent vertices are assigned with the same color, meaning the chromatic number of the graph is 7, and this also means that the number of gates needed is 7 only. To ensure that the result from graph coloring is accurate and efficient in solving the problem, we can create a colored flight schedule. This table was colored based on the graph results to better visualize the conflicts in the flight schedules from the dataset. We can see that there are no overlapping colors in the table, indicating no overlapping airplanes at each gate in a day. From the results of graph coloring, these are the allocation of airplanes to each gate. It can be determined that Gate 2 has the most number of airplanes that can accommodate, and Gate 6 has the least number of airplanes that can stay on that day. Based on the scheduling of the flights, we can see that some flights have short turnaround times and some have long turnaround times. We can conclude that gates that accommodate flights with long turnaround times tend to have the least capacity, while gates that accommodate short turnaround times have the most capacity. It is also important to note that the solution for this problem is not unique. The result is only one of the many possible combinations of colors in the graph. This means that other solutions will present different combinations of allocating flights to airport gates where the number of flights per gate will also differ. The next time your flight arrives or departs on time, thank graph coloring for providing an optimal scheduling. We saw how graph theory can help us solve real-life problems. Whether it be a simple one or not, it only shows that in every connection, there comes a solution.